My name is Dr. Dan Rasky. I'm a senior scientist here at NASA Ames Research Center. And for COTS, I actually had several roles. I was part of the setup team under Admiral Steidel, actually, when the concept for COTS came together. This was back in 2005, early 2005, and working with a number of people at headquarters, which actually then resulted in the COTS program that was run out of JSC. And so we were supporting that activity, both the implementation, the initial concept, the implementation, and then the actual procurements working with JSC. And then also I have worked with several of the emerging space companies, notably SpaceX, on tech transfer so that they could develop the systems that we needed for the COTS program. The study actually, it was Rebecca Kaiser did when she was the leading the Office of Strategic Formulation at headquarters. I think was very, very useful. And this is where they went and did a NAFCOM model for the Falcon 1 and Falcon 9 and came up with a number of just shy of $4 billion when we knew from a number of other sources that SpaceX had spent under $400 million. And I mean, that report is I think, online, but I think it's very instructive. How could we be that far off, over a factor of 10? And by the way, everyone finds that just unbelievable. I found that unbelievable when I first heard it, but the facts are there. And it really has to do with, again, the incentives, the business model that you're using. I think a lot of padding that has, through years of operation, kind of gotten into the model. And cost testing models tend to only go one way. They get more expensive over time. They seldom get cheaper over time, at least for space products. And I think NAFCOM has kind of fallen into that. And so whatever price NAFCOM gave you, that was like that was the lowest price that you were expecting for that project. My guess is that in most cases you'd find actual projects were performed would exceed their NAFCOM price. That would probably be the normal tendency. And so having it, I think that study was very useful to see, okay, there are ways to do this much cheaper, but under the right circumstances. Again, you have to have the right environment where you have essentially a commercial entity that has enough capability and of a startup type mentality that they're willing to take this on. And so not everything would lend itself to what SpaceX has done. But I think there are a number of things that could. And I guess the thought that a number of us have had, including Rebecca, is that, well, if you can identify those projects, okay, and if you can manage to get, significant cost reduction in certain areas, well, that in theory would free up money to do other things that you want to do. So it would allow you to advance your portfolio of projects rather than, having to really, starve the things you are currently running because the resources are too small compared to the requirements of the project. So, but I think that's a very useful study. My guess it'd be interesting to look at other things like now the Blue Origin's vehicle, the New Shepard. Okay, what did Jeff spend, developing that? And you can do the same thing. You can do a NAFCOM model. Okay, what did he spend versus what would we have guessed he would have spent with standard business practices, and see, can you get some more data? We did have one other case I should mention that was run, this is back in 2009, where we were looking at SpaceHab. Because SpaceHab also came in and did more of a entrepreneurial approach for putting in place the SpaceHab logistics module that flew on the shuttle. We found a factor of 8 savings there. Okay, so same ballpark that Rebecca found for SpaceX. So that gave us some confidence. Okay, this isn't just a fluke at SpaceX. This is a real phenomena if the right circumstances prevail, where you can get a private money and more of a startup approach to take on a project. But it would be interesting. Again, Blue Origin would be a good example now. Maybe see at ULA and see what they may see relative to their cost structure for the things that they want to pursue, seeing as they're kind of in this transition mode, and see if My guess is that they're hoping for a number of cost savings, but we'll see if that materializes or not. We realized early on, this is back 10 years ago actually, when we were first working the COTS program, that cost plus contracting, it really misaligns business incentives between the government and the providers. We joke that, the more stupid the government is, the more money the contractor makes. That's kind of the common view, and it's pretty accurate, because what happens is that cost plus, the contractor, he's going to have his costs covered regardless. And so if the government changes its mind or has bad requirements to going in, they get to just get paid to do the job 2, 3, 4 times. And we did a little bit of research. Okay, where did cost plus contracting come from? And our understanding is that actually it came up during World War II, when urgency was the most critical factor in getting a product in place. And so the cost efficiency, that wasn't important. That was way down the priority list, is that we need to get somebody working on this. And when you're fighting a war, that makes sense. Urgency matters, okay? So getting someone to work on a project, even if you aren't quite sure what it's going to be, you're not quite sure about the requirements, but get somebody working on it, so as soon as we understand the requirements, we can have a product, as quickly as possible. That makes perfect sense in that type of environment. And our understanding is that over time, both the government and industry got kind of hooked on this bad practice, because firm fixed price, again, there's lots of models that show that gives you much better alignment of business goals. Firm fixed price, the government gets what it asks for, but has to stick to what it asks for. The business actually can make more than just a fee with regard to what they're doing, so there's more incentive to them, but the government can't be changing what it's doing, okay? But they have to then deliver, okay? So it provides better incentives for the government to be clear about what we want and stick to it, not, wander around, and for the industry to produce and produce well, okay? So it gives you alignment of business goals. And so it looks like, to us, it was just, something was born out of urgency of war that kind of became common practice and probably used too much. And again, I'm sure there are circumstances where, again, cost plus is the best approach, particularly if you aren't quite sure what the requirements are for a number of reasons, and so you're going to have to iterate around. But it looks like the more we look into it, that should be an exception to what NASA does, not the standard approach, and that the standard approach really should be much more firm fixed price, FAR Type 12, commercial purchases, again, where you have an alignment of business goals so that the government wins and the contractor wins. That's what you're looking for, not that, okay, if the government is really, ill-prepared, that the contractor cleans up. That is a situation you want to avoid if you want to incentivize cost effectiveness. And again, it's not a mystery. It's just, okay, that I think a bad practice that kind of got out of hand. The whole design process at SpaceX, at least back in 2008, 2009, when they were really in startup mode, was significantly different from traditional aerospace. In fact, it was well known that people who would come from either NASA or traditional aerospace to SpaceX would suffer a certain amount of culture shock getting used to this startup method of operating. For example, requirements, I never once saw a requirements document when we were working at SpaceX developing the thermal protection system. Essentially, Elon wanted a heat shield for his Dragon capsule. It had to be able to do Earth returns, but he also wanted it capable of doing lunar returns. That was pretty much it. That was the requirement document. And so then we worked in what you might call a collaborative design environment to come up with the heat shield that was compatible with the structure, with the propulsion system, with avionics, and the other subsystems to give a successful Dragon capsule. So there's no formal, at least at that time, there was no formal requirements document that you typically would see under a traditional aerospace approach, where we spend a lot of time putting together fairly detailed sets of requirements, particularly for all the different subsystems. I didn't see any of that. I didn't witness any of it. Now, from from that period of time when they were really doing a lot of development to today, they have brought in more of a production approach. They have gone to more requirements, documents, and configuration control. But at the time, back in 2008, they were very much in startup mode. All other things coming into play. And again, we have, can you get people to move to a certain place? Elon, again, he was able to choose where he put SpaceX. It's no accident. It's in Hawthorne, okay, in Southern California, in LA. He put it there because that's where he had the talent base. That's where the aerospace engineers were that he could, bring into his factory. So he thinks about this carefully. He doesn't just put his factory anywhere. He puts it where he's going to have the resources to make it work. And so Hawthorne was a very attractive place. I mean, you just look at the census data and how many aerospace engineers are in that area. There are a lot, okay. And of course now there are a lot of people that he's bringing in because of the notoriety and the success. But yeah, he had the luxury of choosing a spot that was very fertile ground for him to build a factory. And also the property in Hawthorne at the time was very undervalued. He bought this whole Hawthorne facility, again, for a song. I believe it was Northrop had that facility. They were doing refurbishing of 747 fuselages, I believe. And actually, another story. When I was actually walking with Elon through that facility, okay, September 2007 is what happened. I had crossed paths with Elon at the AIAA Space 2007, and he wanted to talk more about TPS, which actually is interesting at the time because at that time he hadn't flown a Falcon 1 successfully, but he was already looking ahead for a TPS for a Dragon capsule for a much larger rocket. So anyhow, so he and I had crossed paths, and he wanted to talk, and he asked, can I come and visit him at SpaceX? And at that time, they had their facilities in El Segundo, which is 10, 15 miles away from Hawthorne. So I go over to El Segundo and talk to his executive assistant. She said, oh, Elon's over at Hawthorne looking at this new facility, that he's thinking of leasing. And so you can find him here. So she gave me directions. So I hopped in my rental car and buzzed over to Hawthorne. And at that time, let's just say it wasn't very impressive. And anyhow, so I found my way inside, and there's Elon walking around, and it's this huge facility, but there's like trash and old discarded equipment everywhere. I mean, it looks a little bit like a disaster movie set, for Hollywood. Like, oh, this place is going to need some work. And this is in September, and I think it was about mid-September. And so he's asking me some questions about TPS, and we're walking through this facility. And so at one point I turned to him and say, so when are you moving in here, Elon? He says, we'll be in here in October. So this is middle of September. There's trash everywhere. There's the lavatories are non-functional. I mean, you sure a health inspector will allow people in this building? He said, we'll be in here in October. And I remember thinking, when he told me this, no way. Okay, no, not going to happen. Well, I came back in October, and they were in the building. Okay, now, and he already had the layout. He already had the shop areas and the engineers in their cubicles. And I remember the engineers are there working while they're putting up drywall, and while the engineers are working, and so they have plastic, on their desks and sometimes over their head because the mud from the drywall is coming down on their desks while they're trying to work. But they were in October, okay? And so when he puts his mind to, okay, this is going to happen, people move heaven and earth to make that happen. But when they moved in there, that was a kind of a rundown area of LA, okay? So it was right next to Hawthorne Airport. He liked that because he needed to have easy access to air transportation because of his Tesla activities here in the Bay Area. So he'd flying back and forth. So he liked the location. Hawthorne literally almost gave him the facility. I don't know what he paid, but he got a really sweetheart deal on that facility. And now, like I say, anything that's not nailed down in Hawthorne, Elon is buying it and filling it full of people because he's expanded so much. Actually, this is one interesting element that I observed, and this isn't just Elon, but I think if you take a look at Jeff Bezos of Blue Origin, he's in the same boat. and a number of others. And I think it's a key difference that we somewhat struggle with traditional aerospace. If you look at traditional aerospace, a large number of the managers until recently in those organizations got their organizational training in the military. A lot of them, that's where they learned how you organize people, large number of people. That's where you get hierarchy, chain of command. Okay, if you take a look at all these current billionaires, Richard Branson, even Paul Allen, Elon Musk, Dave Maston, Jeff Bezos, they all got their management training in the software industry. That's where they cut their teeth. That's where they saw how you organize people. And that's a whole startup, structure, which is almost at the other end of the spectrum from a military organizational model. Startup mentality is very flat. You do things ad hoc. People work very hard, but it's a kind of an organic structure. It's kind of what I call the pickup game of basketball. So for any of you sportsmen out there, if you're going to play a pickup game of basketball, okay, well, you show up at a gym, and there's a couple things you have to decide on. Okay, first you have to show up at the gym. Two, you have to decide what game you're playing. Is it basketball or football or soccer? Now, if some of you are playing soccer and some of you are playing basketball and some are playing football, it's not going to go very well. So you have to decide on what game you're playing. And then you have no coaches generally, and then people start playing. And if you take a look at organizational theory, you find that we self-organize very well in groups under 160. That this is part of our hunter-gatherer evolution. So under about 160, people are very good if they decide on what game they're going to play and then start playing. They will organize to find out who's a good guard, who's a good forward, who's a good center, and they'll arrange themselves through this organic process to play basketball. And so that's what the startup companies tend to do. They let that natural organizing process occur. Now, the challenge, and Elon so far has handled this very well at SpaceX, if you get over about 160, now you need some superstructure, okay, because people can't self-organize over that amount. And that's where the military came in with their way of organizing large number of people. And typically that's a stumbling point for organizations, getting from essentially under 160, the startup mode, to being much larger. Like I say, to date, Elon's handled that transition very, very well. I know there were a number of people concerned, could SpaceX make the transition from really that startup mode, self-organizing, everyone, pulling towards the same goal, to a large organization where now you need to have some type of organizational structure and directors, you need some level of requirements and documentation to operate. But to date, he's done that as well. It's challenging, and I guess one thing that I've seen that Elon has done, he brought in a lot of production people. Which created, I know, some tension with the R&D engineers, because when they were in startup mode, the kings were the research and development engineers, and once they got into production, Elon brought in people. He brought in, I think, one of the key project managers for Mini Cooper, and this is a guy who was making thousands of automobiles a year. And so when Elon talked to him about making, a few tens of rockets, he could like, tens of rockets, that's easy. Okay, I've made thousands of Mini Coopers, and I don't know if you know much about Mini Cooper, but they can be custom designed, so they can have a lot of different variations from vehicle to vehicle. So he actually brought in people who understood high production, precision manufacturing. And then they have become kind of the kings, particularly in the shop. And if you go out to the shop at SpaceX, you'll see they have these glass cubicles in the shop area, and those are all the production engineers. So they can look out from their desks at any time and see how kind of the whole, shop area is going. If they see a problem somewhere, they can see it and address it immediately. Whereas the R&D engineers are next door at their cubicles. So Elon, I guess, did enough thinking as to how did he want to handle the work environment to get the results that he wanted. Co-location, and again, I'm kind of two flavors of co-location, because I've had the opportunity at NASA to have a very reasonable office, and it's nice having your privacy and so on. But I did see the effectiveness of that cubicle approach and the co-location at SpaceX. There's no doubt about that as far as people being able to work very, very efficiently and effectively with one another. And to tell you the truth, I was actually quite skeptical at first. That, well, how can you hear yourself think here? And there's all this commotion. How are you going to get any work done? And it does take, I'll say, a few weeks to kind of get used to it and kind of adapt. And I guess if you're very noise sensitive, that might be more of a problem for you. But I think there's no doubt of how efficient that is when, again, you have a clear project that you're working on. And again, one of the big advantages SpaceX has is that they have a pretty clear line of products they're working on, okay? NASA, we have a very broad array of different projects and hardware and other things that we're working. SpaceX, and what they have their Falcon 9, they have their Dragon. I mean, they have, you can count them on one hand, the different primary products they're working on. So it makes it a little bit easier. Everyone's working on the Falcon 9, okay? So, well, everyone's working on the Falcon 9. Yeah, there's a lot of commonality there. When you have a large array of project and activities like we do at NASA, accomplishing the same co-location is, I would imagine, challenging, okay? So unless you have very large projects. SLS, I guess, is probably a good example, but now you have people around the country, okay? So co-location is, again, a bit of a challenge there. Now, SpaceX does have several facilities. They have the McGregor test facility, but those are clear demarcations between designing and building the rocket in Hawthorne, and then at McGregor testing the rocket, okay, and then at KSC and eventually at Brownsville launching the rocket. So those are really major, functional differences. And so NASA doesn't have that luxury because of our history and the distribution of centers around the country. The political interest in keeping centers around the country. There are some natural challenges we have that SpaceX doesn't. But nonetheless, there's no doubt that when you have people working on a project, okay, and that's their primary role, if they're co-located, I think there's no doubt from what I saw at SpaceX that is very efficient for making progress. But what you will find is, it's this master apprentice model. This is classic. And it does work very well, okay? And again, we have our student programs here at NASA, which I think in many cases work in the same vein. But yeah, if you have someone who has quite a bit of an experience teamed with someone who's young, that can be a very dynamic collaboration, because the person who's young doesn't know all the things that can't work, or to not ask, silly questions, and so they'll try things. And then the graybeards, well, we've seen what works and what doesn't work, and if you can get that right dynamic, you can make tremendous progress. And that's a kind of a classic lineup that I saw a number of times there. But again, it's all ad hoc. It's not, you're assigned to work with this person. It's what driving the driving organizing element is that you've got these top-level requirements from Elon, very top level. Make me a Dragon capsule that will, survive Earth reentry and be able to come back from the moon. All right, that's it. Everybody get that? Okay, because that's what we're going to do. So you have these very top-level requirements. So people are all working to those top-level requirements, and it makes it possible then for really this impromptu and kind of ad hoc group formation. One thing that I had hoped for and that we're starting to see isn't that NASA can duplicate what SpaceX does, because SpaceX, again, has certain advantages that NASA doesn't, okay? But what I was hoping to see, and I think we're starting to see that, is what can we do, okay? What practices can NASA adapt? There's some things we can, there's some things we won't be able to because of our different environment, our different history, our different role. But I think there are some things, and kind of going back, in some ways, back to the Apollo days. If you take a look at kind of the environment that NASA had in Apollo, it was kind of what, in some ways, Elon has with his young engineers and some graybeards. But you had, people trying things and what works and what doesn't work. I think over the years we've gotten into a very, you're talking about risk, very risk-averse profile, and where I call it full matrix engineering, that all concerns that anyone can raise have to be chased down to 100% before you can make any decision. Okay, so you have like a full matrix of all the things that may be pertinent to a certain decision, and you have to fill that entire array before you can make a decision to go forward. And there's times when that makes sense, but it doesn't make sense for everything we do. SpaceX uses a sparse matrix, okay, 51%. Okay, when we get to 51%, okay, enough, we're going to make a decision, and then we're going to try it and move on. And so I think there are things that NASA could do, some, Explorer class projects, particularly, again, for fresh outs and people first getting into the business. Let them cut their teeth, doing some low cost, low consequence projects to fly some stuff in space. And now with things like CubeSats and some of the other things we have available, there's opportunities for that, because there's nothing like flying your first hardware and going through that entire design cycle. I had a chance to do this before I came to NASA, so I saw how both invigorating and terrifying that was. But once you've gone through it, then it kind of whets your appetite. Okay, we can do this again. We can do this again. And if you've never been through it, and I've seen some of my colleagues at NASA who've been here for decades and have never flown anything that they've worked on, for decades. Well, that gets you in a very risk averse, because now anything you do fly better work, or this is maybe your only shot. And so, opening the door so you can have more flight projects that are lower cost, lower consequence, particularly for people first coming into this industry, I think would be very helpful and would be quite invigorating for the existing staff. So that's maybe one of the things that we could adopt from SpaceX. Working there, then after that, I realized that, this is part of their process. As soon as they get to, we would joke, 51% probability, they would make a decision and move forward. Now, you might ask, well, what would happen if that decision turned out to be wrong? Then they backtrack. Okay, so what they do, they make a decision which allows you to move ahead, and then you verify, okay, is that the right decision or not? If it is, you keep going, but you keep making decision after decision after decision like that. And if once you move forward, you find that there's a problem that you hadn't anticipated, then you backtrack. Okay, until you make another decision and try it again. So it allows you to progress very rapidly. They also make extensive use of the internet. And I'm sure they do at least as much today as they did back in 2008. If they hear about a new technology, the first thing they do, they're on the internet. Okay, they're finding articles and papers that describe what that technology is, who's working it, who's doing the research. They'll make contact with whoever is doing that work. They'll have telephone discussions, maybe invite the person in, maybe take a trip to see them, get prototypes in place. And they would use the internet for all their prototyping. One of the big sources of equipment is McMaster. And I saw where we would see an interesting technology and literally within a week or two have a prototype on the floor of that technology to start looking at. A week or two from when they first heard about it to tracking down people to getting on McMaster and ordering equipment in to be able to test it. And so it was just astounding how fast they would move. The other example I'd like to point to is once we did the make decision for Pika, we had to set up a TPS lab, and literally from scratch. I mean, what we had was a large room because the facility at Hawthorne was very large, but we had a large section of the facility with essentially concrete floors, walls and lights, and that's it. I mean, there was nothing in that shop at all. And over the course of 9 months, it went from literally an empty space to a world-class TPS production facility where they were producing 4 blocks, large blocks of Pika in a big oven at a single time, so a big batch mode, and much better than any of the outside vendors had developed to that point. So in the course of 9 months, it went from being essentially an empty room to having the best Pika fabrication facility on the planet. 9 months. And again, if you would have told me, based on my NASA experience, you could make that much progress, I would have said, no way. Maybe 18 months if you pushed really, really hard, but we did it in 9 months. So that was quite astounding. So the whole pace of development is just at light speed compared to what you're used to in traditional aerospace. And it really does take a number of months to get used to that, to get used to how rapidly things move, how rapidly decisions are made, the whole, try it and verify, move forward or step back approach, and the whole collaborative design environment between the different subsystems. Again, one of the design approaches SpaceX uses is rapid prototyping and test and failure. And I'll give you one example that actually I thought was quite interesting. One of the times we had a little difficulty between two groups had to do with the temperature limit that we were looking at for the bonding agent for the Pica heat shield to the structure. And we were given a number from the structures group that looked low, that they wanted, we had to specify that the bond was below a certain temperature. And we were suspicious that that number was too low. And so we went and talked to the structures group and said, oh, no. I still remember the gentleman saying that the composite structure that they're using for the carrier structure for the TPS, it turns to butter above this temperature. And myself and another gentleman were walking away, and we said, we don't believe that. And this gentleman actually was Andrew Chambers. He said, we're going to test this. And we had this big oven where we made the Pica billets, and it could go up beyond the temperature that we wanted to actually use, and way beyond the temperature they said was the limit of this composite. So Andrew actually was able to go get some samples of this composite. We set up a jig, okay, and this took 1 day, okay. So we got these samples. We set up a jig in the oven where we highly loaded these samples so that they were under great strain at room temperature, okay. Went out of the oven, closed the door, and cranked up the temperature. Okay, so we first cranked it up to the point where the gentleman said this turns to butter. And what we would do is that we'd open the oven, run in and measure the deflection because it's hot in there, and then run back out and close it again. And so we first got to the temperature, we said it turned into butter, okay, and they hadn't budged at all. And then we went up to the temperature that we wanted to use, and they had budged a little bit, but hardly at all, okay. So then we went back to this gentleman, okay, in the composite group and said, well, we just ran a test relative to these limits you're giving us. It didn't turn to butter at this temperature. It looks like it's fine up to this. And that's when the gentleman said, well, yeah, but we just can't trust you guys. So they were giving us an artificially low temperature because they were worried that we would violate that temperature limit. But what actually brought that to light was this rapid prototyping. We literally did this in a day, okay, with the things that we had available, okay. We went and did it, and okay, you said that it turns to butter here. We're going to check that and see if it does or doesn't, and it didn't. And that's an example of how they work, okay. If someone gives them a requirement or some type of a parameter, they are prone, well, let's see if that's the case or not. Let's put together a jig, let's put together an apparatus to see if we verify what we've been told. Does it work this way or not? And they can do it very, very rapidly. And what happens is that you're able to learn very quickly. And for example, another one that we did on the way to scaling up Pica, to go from essentially an empty room to a world-class, Pica shop, Pica factory, we did it in 3 phases. We first did first phase, prototype phase of things about the size of a coffee cup, just so we could transfer the process to the SpaceX team. Okay, here's how you make Pica on small scale. Then we had to go to a scale up of a full-size billet, but we did that with a prototype unit, and because we had some concerns about temperature requirements and uniformity. And so we built a prototype unit. It took us about 3 months, but we built a custom furnace that we could monitor very accurately the temperatures, the state of the material in the device. And after doing several billets out of that, we were able to then go and design the full-scale facility. But it was going through and very quickly doing try this, does it work? Okay, learn, go to the next size, go to the next size. And at each step, we learned very important things that were working, and things that weren't working, things to watch out for. We had a couple gotchas on the full-scale billet prototype that we were able to resolve. We were seeing some funny behavior for a while on how some of the solvent that's part of the process on how it was modifying the phenolic. And we were scratching our heads for a couple of weeks, and we ran some tests and found out what it was and modified the approach and got it to work on a full-scale billet. And by the way, I should mention that was the first time that anyone had ever done a full-scale Pica billet. Even the outside suppliers had not ever accomplished a full-scale billet, and we were able to do that through this prototyping. But doing that rapid prototyping and testing, it allows you to identify, what's important, what are the things that you don't know about that are going to bite you, and address them early on before you go to a full-scale facility. Where now, if you have a problem, now the options you have to fix a problem are far fewer and far more costly than at a smaller scale. So that was one thing that you'd see over and over again. They do it on all sections. I saw that in the TPS area, but they do it for structures. They do it for engines. They try to prototype at the smallest scale that they can initially, and then work their way up to full scale, and do it as rapidly as possible with 51% confidence at each step along the way. Also, I think, Blue Origin now, Jeff Bezos, he also, similar to Elon, and I don't know if you know any of his history, but he was actually planning to do space work back when he was in high school. He wrote a paper, apparently, saying that he wanted to do, great things in space, but that first he needed money. So he formed Amazon to get the money so that he could do stuff in space. And that's what he's doing with Blue Origin. And his approach has been very interesting compared to Elon. Elon built his rocket from the bottom up, which is how most people do it. Jeff is building his rocket from the top down, starting with the capsule, the New Shepard, and then the stage that he just flew, which actually is a second stage. It has to do with his BE-3 LOX hydrogen engine. Okay, it's actually intended to be his second stage, and then he developed a BE-4 engine, LOX methane, which will be his eventual first stage that ULA is looking at to actually upgrade the Atlas V. So Jeff is actually building his rocket from the top down, okay, but also making incredible progress at this point. So the fact that we have, as I mentioned now, really 4 serious contenders: SpaceX, ULA, Blue Origin, and Orbital ATK. What are the commonalities between those 4 organizations? How have they decided, to pursue this? What strategies are they pursuing? What are the commonalities between them and their hiring practices, their promotion, how they incentivize their workforce? What markets are they going after? How do they work with the government? I mean, you've got actually a very, fertile ground for some really good business case studies. And again, pulling out what are some of the things that NASA could adopt. Again, we won't be able to adopt everything, but what are some of the things NASA can adopt, and what type of projects could NASA pursue where you could beta test some of these ideas and see how they work out. And I guess that's one other thing that I think would make sense. The part of the software industry, this whole idea of beta testing. And any of you who know software, you get something that barely works and you put it out on the market. It's called a beta. Because what you want to do is see, well, how is it responding to the customers? What's important? What's not important? And I have enough friends who are in the software business that they find that's immensely valuable, because a number of things that you may think are important, you find out aren't. And then a lot of the things that you thought weren't important, are. But the only way to get that information is to get something that's somewhat working and get it out working and get the feedback. And so again, I think you're seeing the Jeff Bezoses and the Elons and the other folks, and now at Tori Bruno at ULA, they're willing to beta test things, try it, see how it works. Now, if it works well, fine. Now adopt it full-heartedly. If it doesn't, adjust it. And whereas we're very reluctant to do that at NASA, we usually like to go for we call them the Battlestar Galacticas. We like to go for that really big, mission. And again, there's a number of reasons for that. The Webb Space Telescope, okay? I mean, you can't just beta test Webb, okay? You have a significant commitment, and so you want it to work. We've had experiences like with Hubble, okay? When these very large projects don't work, there's a lot of both brand damage and difficulties to be faced when we have our large programs that don't work. But how do you make use of beta testing where you can, again, on levels and on programs that are low enough consequence to try it out before you move it in. And so again, looking for opportunities for beta testing different organizational designs, different incentive structures, and so on. And I know that's easy to say and much harder to do, but that's one of the lessons that you can see from these companies. The whole collaborative design environment really does set the stage, along with the very fast-paced approach, both for getting equipment and making decisions. And Elon makes it very clear what he wants to have accomplished, and then the teams work together, looking at the different subsystems and how do you make compromises where you need to achieve the result that Elon wants. And one of the things that really enables that is the whole incentive structure at SpaceX. And this is one of the things where we have, I think, some real challenges when you get into an established bureaucracy. Established bureaucracies tend to have certain organizations, certain silos, and the incentives for the people working in those organizations is to benefit their particular organization. And so in the mix, the overall goal of the program can get lost relative to making decisions that benefit certain parts of the organization. At SpaceX, Elon was very aware of this, and so he deliberately would not pay that high of salaries. A large part of the compensation for anyone who went to work at SpaceX was stock options. And so your real compensation comes when the company succeeds. And that does a lot to align essentially business goals and interests, that even if you're a propulsion individual, you want the TPS to succeed, because if the TPS doesn't succeed, then the company doesn't succeed, and your stock options aren't worth anything. So it creates a collaborative situation where people are pulling all towards the same goal, and they're willing to make compromises. One of the interesting things that I witnessed is that on the first Dragon capsule, the C1, there was a problem with one of the bulkheads in the pressurized volume, that one of the bulkheads had been undersized. And the structures group actually came to the TPS group and asked if they could place a spacer to put some of the loading of that bulkhead onto the TPS structure, because we had margin in the TPS structure. And I mean, I would never, see something like that at NASA. You'd go and redo the whole bulkhead. But what they wanted to do, they wanted to get the capsule out, and they had done the analysis and said, okay, we should be okay on this capsule to transfer some of the loading, from the bulkhead to the TPS support structure. And again, that, allowed them to go forward. And the TPS guys took a look at it and decided, oh yeah, it was within range, and so it was no problem. And again, so that type of collaboration of give and take on the different design, challenges and solutions allows you to really move along quickly. And the other piece of it has to do with really the rapid pace of both acquiring information and system data and making decisions. And I had this one situation which has been related in several other areas, but I think it's worth noting. When I was first working with SpaceX, probably a couple months in, and this is one of the first meetings that we had to make a decision on make or buy for the heat shield, for the Pika heat shield that was going to be used on Dragon. And I was still the new kid on the block, but we had a design meeting, must have been about 10 or 11 engineers and Elon, so we had all the major subsystems represented, propulsion, TPS, structures, avionics, and then Elon. And so we the group was discussing whether, make or buy for this TPS material. And I was at that time just listening because I was the new kid on the block, and okay, seeing how does this type of an organization function. And at one point, Elon looks over at me and says, "Well, Dan, what would you do?" And so I explained to him, well, based on what I'm hearing, I would actually do a make, not a buy, and here are the reasons for it. Explain that it wasn't that hard a process, and that it would allow them to optimize the Pika both for Dragon and then also have the capability for making TPS for future needs. And so after explaining this for about 3 or 4 minutes, Elon leans back. No one says anything. Elon leans back and says, "That's what we're going to do." And that was the end of the meeting. And everybody stood up and left the room. And I was somewhat shell-shocked, like, what? This was the first meeting we had on this. We hadn't had any prep meetings. It's the first time that we were all together discussing this. And that was it. And everyone walked out the door and went to work on, okay, how do we make Pika at SpaceX? It took me several days to get over that wow, okay, did I say the right thing? At NASA, we would have had, many meetings looking at, okay, what are the options? What are the metrics we need to be concerned with? What are the impact on other subsystems before we came to a critical decision of make or buy on a very important component. The incentives are absolutely essential. If people aren't doing what you want, you need to look at what are the incentives in place, and you need to change the incentives so that you get the behaviors that you want. And I think looking at what Elon's done and some of these other startups, I think that's really clear. Second is, I think, understanding the different business model that they're approaching or that they're using. There's really this flat startup software-based business model in contrast to more of a military hierarchical model that traditional aerospace is used. I think that's the other huge difference that you're seeing. And then third is their collaborative design approach combined with the rapid prototyping and the sparse matrix engineering. Okay, those three together are just really potent. It's a potent combination to really advance. So I guess those are the maybe 5 takeaways.